Have you ever really stopped to think about what's going on inside a battery? Or how we can use electricity to create pure metals? Well, it all comes down to this hidden chemical secret that, believe it or not, powers everything from our phones to our biggest dreams for a cleaner future. So let's dive in.
I mean, think about it. We use these things every single day, but what is actually happening inside this little device? What's the magical process that's creating power seemingly out of thin air? Okay, so the answer is one single really powerful word: electrochemistry. Yep, that's it. It's the science that bridges the gap between chemical reactions and electrical energy. And honestly, it is the engine driving so much of our modern world. So, let's pull back the curtain on this secret. What's the core idea that actually makes a battery tick?
Okay, so at its heart, electrochemistry is really a two-way street. On one hand, you have chemical reactions that just happen. They're spontaneous and they release energy that we can capture as electricity. But then on the other hand, we can flip it around. We can use electricity to force chemical reactions to happen, reactions that would never occur on their own. So this two-way street idea gives us two very different kinds of tools. First, you've got the galvanic cell. This is your battery. It takes a chemical reaction that wants to happen anyway and turns its energy into electricity. But then you have its opposite, the electrolytic cell. This one uses power to make a chemical change happen, like when we're creating pure aluminum or sodium. All right, let's zoom in on that first one, the galvanic cell. How in the world can we get electricity out of a simple chemical reaction? Let's break it down. To really get this, we're going to look at a classic, the OG of this stuff, the Daniell cell. It sounds complicated, but it's a surprisingly simple setup. All you need is some zinc, some copper, and a couple of salt solutions. Okay, so here's how the magic happens in 4 basic steps. First, you've got the zinc electrode, which we call the anode. It starts giving away its electrons. This is called oxidation. You can kind of just think of the zinc dissolving. Now, second step, those electrons that just got freed up, they need somewhere to go. So they start flowing through a wire that connects everything. And get this, that flow of electrons is your electrical current. Boom. Third, the electrons finish their journey at the copper electrode, the cathode. Here, copper ions that are floating around in the solution grab those incoming electrons. We call this reduction. And finally, and this part is absolutely crucial, you have the salt bridge. It's like a traffic controller for ions, letting them move between the two sides to keep everything electrically balanced. Seriously, without that bridge, the whole thing would just stop.
So the big takeaway here is that this cell isn't making energy out of thin air. Not at all. It's simply converting the chemical energy that's naturally released during this whole back and forth, this redox reaction, into the electrical energy we can actually use.
Okay, so that's how we get electricity from chemistry. But what about that other side of the coin? Let's flip it and see how we can use electricity to drive chemistry. And that is exactly where electrolytic cells come into play. I love this analogy. If a battery, a galvanic cell, is like a waterfall where the flowing water naturally generates power, then an electrolytic cell is like hooking up a giant pump to force that water all the way back up the hill. You're using energy to make something happen that wouldn't happen on its own. So you might be asking, why would we want to do that? Well, this process, which is called electrolysis, is a massive deal in modern industry. It's how we get super pure copper. It's also how we produce really reactive metals like sodium and aluminum, stuff that's just incredibly hard to get out of its natural state any other way. All right, now let's talk about where this whole electrochemical process happens all around us every day, and usually when we really, really don't want it to. Yep, I'm talking about rust. Believe it or not, when iron rusts, what you're seeing is an electrochemical reaction in action. A patch of rust is basically a tiny, unwanted galvanic cell, a little battery you never asked for that's just slowly eating away at the metal. It has all the same parts we just talked about. And check out how closely this mirrors the Daniell cell we just looked at. Some random spot on the iron acts as the anode, and it starts to oxidize. Remember, that just means it's losing electrons. Those electrons then travel right through the metal itself. The metal acts as the wire. To another spot, the cathode. At that spot, oxygen and water in the air grab those electrons. And the final step? The iron ions that are left behind react with oxygen and water, and that's what forms that flaky reddish-brown stuff we all know as rust. So, electrochemistry explains the good, like batteries, and the bad, like rust. But where is all this science headed? Let's take a look at how it might just be powering our future.
Okay, let me introduce you to the fuel cell. Think of it as a special kind of galvanic cell, like a battery that never dies. See, a normal battery has all its chemical fuel sealed inside, but a fuel cell, you just keep feeding it fuel like hydrogen, and it'll just keep generating power as long as you keep that fuel coming. But here's the really mind-blowing part.
It's efficiency. A typical hydrogen fuel cell can turn chemical energy directly into electrical energy with, get this, up to 70% efficiency. That is just astonishing. And just to put that number in perspective for you, your standard thermal power plant, the kind that burns fuel to make steam to spin a turbine, clocks in at around 40% efficiency. So fuel cells, by cutting out all the middle steps, are nearly twice as efficient. That is a massive, massive leap forward. And that incredible efficiency, that's exactly why fuel cells are right at the heart of this huge idea called the hydrogen economy. Just try to picture it, a future where our cars, our homes, our factories are all powered by a fuel that's not only renewable, but also totally clean. Because that is the ultimate promise of hydrogen, right? When you use it in a fuel cell to make electricity, the only thing that comes out the other end is pure water. No CO2, no nasty pollutants, just water. So, you see, from the little battery in your TV remote, all the way to this grand vision of a hydrogen-powered world, it all comes back to electrochemistry. It's this silent, powerful science that's all about turning chemistry directly into electricity. Which leaves us with one really exciting question. What are we going to power next?